Hello everyone. In this video, I'm going to be talking about benzene ring chemistry, a brief introduction to it before we really get into some of the reactions, aromaticity, and a couple other things that might come up as I'm discussing this. And this is going to be for the backbone, the foundation of your entirety of test 2 material. So the majority of test 2 content has to do with reacting with benzene rings and how benzene rings um, how we're able to react them with different compounds. So a big portion of understanding how this works is understanding aromaticity, which is a special type of stability that benzene rings have and other compounds have, that really explains why they're so stable and why they're so difficult to react with different materials or different reagents. And if you remember, the ability to react has to do with how unstable or the instability of the two, or the different types of reagents that are present. So we're always going towards stability. We're always going towards a lower energy. So reacting with benzene rings is different because you would assume, like double bonds, that they have, the ability to react with different things like HBr and H3O plus and acids and so on and so forth. But you'll find that if you just simply introduce these reagents to a benzene, like a solution of a benzene, or anything else aromatic, it won't really react. And you have to do special types of conditions in order to allow it to react. And that's what we're really going to be talking about and kind of just introducing in this video for the most part. So we keep hearing this word, and the word is aromaticity. So what exactly is aromaticity? Well, aromaticity is, let's try to define it. Okay. Aromaticity essentially is a special type of stability that is given to molecules that have certain subset of features. Okay, and they have to have these features in order to be considered aromatic. And there's three classifications. Okay, we have molecules that are weird. We have molecules that are aromatic, non-aromatic, and anti-aromatic. Okay, so we have these three classifications that we can, classify all molecules. We can classify all molecules within these three. Okay. Now let's just get through the nitty-gritty. Let's define some things, and then we can talk about it. All right. So I'm going to call aromatic AR just for short, and anti-aromatic AA for short. Okay, get used to these short notations. So to be aromatic or anti-aromatic, there's certain things that have to be present in the molecule, certain characteristics. First, and very common thing that you'll see is they have to be cyclic. Okay, so cyclic. This is being so weird right now, and have to have conjugated pi bonds. Okay, that's the first rule, and these rules are not in any particular order. It's just I'm listing them 1, 2, 3, 4, whatever. Okay, but there's certain rules that have to be present in order for something to be aromatic or anti-aromatic. Okay, and we'll talk about what's the difference between all these different subsets later. They must be planar, so every carbon within, very important, within the ring is sp2 hybridized. Okay. Third thing, every atom is in a p orbital. Right? Some of these rules are just, honestly, number 3, I always suck with hybridization orbitals. It's not particularly important to fully understand that what she'll really test you on are like rules number 1, rules number 2, and let's see. And number 4 is a kind of not as important, but it's conceptually very important. And then delocalization of energy. Okay, delocalization of charges really, to promote a lower energy state. So what this number 4 means is, does the structure, it may have all these other features, but does the structure actually become more unstable as a result? So there's certain examples where it'll come out to be more unstable um, as a result of all this. So that the main things, though, there's certain things that she'll pick on that you need to really be comfortable with, like number 1 and number 2, and we'll see examples of that, and we'll see examples number 4, this delocalization, the resonance. Okay, so number 1, cyclic conjugated pi bond. So I have a benzene ring. So I haven't benzening you for a while. Okay, so now we're seeing him again. We have a cyclic benzene ring, and it has conjugated pi bonds. So I have this pi bond, this pi bond, this pi bond. They're resonating with each other. And if you recall, a benzene ring can be written like this because of the resonance. You can write it as a donut. So that's the donut form of a benzene ring. This is a very easy way to just write it, and you can always write it like this. No situation really where you have to write it like this, unless you're doing mechanism and you're using a particular setup of the double bonds, but it really doesn't matter. Cyclic conjugated pi bonds. Cyclic and conjugated means you have a certain amount of pi bonds that are able to resonate with each other, and they're interspaced like this, with they're not back-to-back pi bonds, but they're, we have pi bond space, and you have a certain number of them, and that's conjugation. Okay, we'll talk about conjugation more. You'll see that more in test 1, or you will have seen it. So I'm making these videos ahead of time. Planar, right? So planar meaning everything's sp2. Every atom is in a p orbital. That's a given. That's kind of a given. If you have these other things, it's a given. I haven't seen really many examples where you have all this and this is not also true. And then delocalization of charges to promote lower energy state. So does the resonance or the resonance forms that allow everything, to be cyclic and conjugated and planar, do all those things, after considering all that, does it help promote the stability, or does the actual, to get rules number 1, 2, and 3 actually make the thing more unstable while getting these 3 rules down? That's kind of what 4 is talking about. The whole thing is to make this more stable, and so if it's ending up less stable, it's kind of defeating the purpose, and it won't really be aromatic. Okay, so aromatic special stability. Now, non-aromatic is essentially, one of these rules are not present. Okay. So one of the rules are just not present, and so you have to have all these 4 be true in order to be aromatic or anti-aromatic. If not, if it's not cyclic, if it's not conjugated, if it's not planar, so if you have something that's not within a double bond within the actual ring, then that's not aromatic. Okay, it's non-aromatic. Okay, so those are those rules. And then now let's just quickly jump into, I'm going to explain, but I'm just going to put the rule down. We're going to say the difference between aromatic and anti-aromatic is the number of pi bonds. Okay, and they fit into certain formulas. All right, so aromatic is characterized by what we have is the 4n plus 2 rule. Okay, and anti-aromatic is characterized by the 4n rule. Okay, and where n, right, can be 0, 1, okay, and 0, 1, and so on and so forth. Okay, and then over here where n can be 1, 2, so on and so forth. Okay, so what does this mean exactly? All right, so let's take the benzene ring, for example. It's aromatic, it's not anti-aromatic. Okay, the benzene ring has 2, 4, 6 pi electrons. Okay, so it has 2, 4, 6 pi electrons, and essentially I count the number of pi electrons that are in a structure that I'm considering. Okay, and I say, okay, it has 6, and then I see plugging in 0, 1, 2, 3, so on and so forth can I get the number 6? And so I'm testing this with these formulas. So I see 4n plus 2, okay? If I plug in the number 1, I get the number 6. So I know that the benzene ring is aromatic. And if I look at the anti-aromatic formula, I can never get the number 6 from this formula. I can only have multiples of 4, 8, 12, so on and so forth. But this one I can have, multiples of 4 plus 2, okay? And 2 itself, because if this is 0, right? Special times where you have only 2 pi electrons and you have all these things and it's aromatic. But this is a very simple example to show you how to classify between aromatic and anti-aromatic. And this is the only difference between them. Okay? So aromatic has a certain number of pi electrons that you can plug in 0, 1, 2, 3, 4, blah, 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 and get the number that you counted. And that's all you're doing. You're just trying to get the number that you counted from the formula and plugging in the numbers. Very simple, right? And then anti-aromatic would just be if you had something that had 4 or 8 or 12, so on and so forth. Okay? And that's pretty much it. So aromaticity is just a special stability given to cyclic conjugated compounds, and it's a feature of these compounds that stabilize them via the pi bonds and the partial pi bonds, and that has to do with the resonance. Okay? So just slow down, try to replay that if it's not coming to you the first time. And that's essentially the summation of all these rules. All right. The final thing left to talk about with this is, how do I know what's more stable? Is aromatic more stable than anti-aromatic? Is non-aromatic more stable than aromatic? Blah blah blah. And essentially, what we have is aromatic compounds are more stable than non-aromatic compounds, and anti-aromatic compounds are less stable than all of them. Okay. So whenever you're ranking based on stability or the energy of the compounds, we're going to be ranking in this order. Okay, aromatic, non-aromatic, anti-aromatic. Okay, and something I left out. This is called I believe actually, this is called Huckel rule. All right. So this formulae are a feature of Huckel rule. Okay. So here's the stability order, and these are how you calculate it, and these are some of the characteristics of a aromatic or anti-aromatic compound. And non-aromatic is just anything that is missing one of these features. Okay. So if it's not a cyclic planar ring, then it's non-aromatic. If it's just a straight chain, it's non-aromatic. It doesn't matter if it's conjugated. It doesn't matter, blah, blah, blah. It has to be cyclic, it has to be planar, it has to be conjugated, and it has to have these other two things. Okay? But those are the main. So this is important to understand conceptually because it makes a lot of sense with when we start doing the reactions, the kind of things that we have to do in order to react the benzene ring with certain reagents. So, for example, I'm going to clear this now. For example, benzene ring, I react this with our friend HBr, which previously reacted with a double bonds to have a monobromination on the most substituted carbon. This will not react. No product. It will remain as the benzene ring. So how do I brominate a benzene ring? How do I do different things with the benzene ring? And that's what this whole test is about, and this is why we preface this with the aromaticity and the stability discussion. So I think that's going to be the remaining. That's all that matters for this video. And in the next one, we will be jumping into reactions and really getting into the nitty-gritty of it. Actually, I think there's something else I should cover in this video, actually. So I guess I might as well, since this will be like kind of the conceptual overview video. So when we're substituting benzene rings, you'll find in the reactions, this is gonna be kind of like a secondary component to understanding the reaction. So one thing that makes this exam harder is that benzene rings, we have to look at different locations of where substitutions occur and can occur. So if you recall from last semester, I briefly introduced, very, very briefly, that there's certain locations on the benzene ring that we can describe relative to each other. So I have this, and let's say I have this, okay? So I have all these R groups coming off this benzene ring, okay? And we have certain descriptions for each one of these, okay? So let's say I'm talking about every position relative to this position right here, okay? So every position relative to this one, right? What we have is that this position right here is called the ortho position. This is the meta position, and this is the para position. Para is on the opposite side, ortho is directly adjacent, meta is one away. Okay, very important descriptors for the varying positions. Okay, now these are going to be important because when we talk about benzene ring substitution, you're obviously, if you recall from how Bean does her exams and how we do things, we're going to be reacting things with multiple reagents. So she may react, you may do one thing, you get a benzene ring with a bromine on it. Then the next reaction comes and she's making you add an R group to it. And the next reaction comes. And that's in between these reactions, it's simply not just knowing what is added, it's knowing, where it's added. So I may have, something added over here, and then I have to decide based on my knowledge of how this works and the concepts that is it going to be adding into the ortho, is it going to be meta, is it going to be para, how does this work? Okay, so so certain things I just to now discuss is to talk about activating and deactivating groups. Okay, so you're going to be learning all the different types of groups that we can add to a benzene ring, how to add them, and so on and so forth. And these groups will fall into different categories. So we have activating, right? Activating groups, and then we have deactivating. Okay, deactivating. And I'm going to pause for a second. All right. So activating are essentially additions to the benzene ring that are capable of donating electron density inductively or via pi bonds directly into the ring. Okay, so that means any group that has electron density or an inductive ability, and it can donate inwards. Okay, and thereby activating the ring. So examples of that is if I have like a benzene ring, okay, and substituted on it, let's say I had an OH, okay, and you'll see a common trend among all activating groups besides the inductive ones, that they have a pair of lone pairs on the atom that's directly connected to the benzene ring. So the atom that's directly connected to the benzene ring has a lone pair, and this lone pair can go inwards into the ring, and obviously a bunch of resonance structures will result, will follow. Okay, so I have all these, different resonance structures that will come out of this, and essentially this can go into the ring and resonate. And that's going to be the same thing whether it's OH or NH2, okay, or if it's OR, right? Anything like that. So you get the point. And then we can also have things like R groups themselves, like CH3, for example, which don't have lone pairs on them, but they can inductively, like we said before, carbon groups are donating groups, right? They're like electron sinks, and they can donate inductively, their electron groups. Okay, they can donate inductively their electron density. Okay, so these are all different examples of activating groups, and we can rank these activating groups in terms of their ability. Well, I'll do that later, but there's different strengths. Okay, and now for deactivating groups, they're the opposite, right? So activating groups have lone pairs that can go inwards, or inductive ability to go inwards to the ring. So I'm going inwards to the ring. And then deactivating, as you might guess, is going outwards, right? So I'm going, I'm bringing the electron density out of the ring, right? And that obviously means that I have groups that have structures that can perform resonance that can go outwards. So instead of going inwards, I have something, for example, like a carbonyl, right? Carbonyl. So a carbonyl, the density from here can resonate over here and go out, and this can go up, right? So because I can go out of the ring, this is a deactivating group, right? And there's many different types of these. You have things like, you know, right? We have, SO3H, right? Or we have, NO2, right? Or we have the CN. This is also one. So anything that can essentially, something can come here and I can have this resonance outwards, right? Resonance outwards, resonance outwards, all these different structures. So that's the whole name of the game here. Okay, the ability for electron density to go out of the ring into a different structure. Usually, it's a stable structure. Okay. Um, and now let's discuss how these groups will relatively direct the addition of other groups. So if I'm having this ring right here, for example, and I'm reacting it with a particular reaction, it's going to direct the location relative to it where the reagent is going to add, right? So if I'm doing like a addition of Br, OH, and other activating groups are what we call, well, not what we call, but they're ortho para-directing. Okay, and I will show all of this or how this makes sense. Okay, we'll look at the resonance forms soon. These are ortho para-directing, and deactivating are meta-directing. Okay, right? And so this means if I have an OH or I have any other activating group, it's going to add to the ortho or para position, right? And I'm going to underline para here. Although there are two ortho positions and it might seem like statistically it's more likely to add ortho, right? There's always two ortho positions to relative to a particular group. But the para position, what's very important is stability, right? And a big part of stability that we've learned over the year and last semester is steric hindrance, right? So para is the farthest away, and therefore it's the most likely substitution because it has the least steric hindrance, and the groups are farthest away from each other. You have the least electrostatic interaction. Okay, so para is the most percent of the product is going to be para. Right, and we're always going to be looking at the electrostatic interactions between the different groups, and that'll help guide you on top of all these other things, the right location. So between ortho para, we're looking at which one is least sterically hindered. Okay, para may not always be the least sterically hindered. You might have other groups here, so you have to consider all those things. All right. And then you have meta directing, and this is just always going to be meta. There's not really much you can do. There's no really decision making that you can make between the two. It's only meta, okay? And it's for deactivating groups. All right. So now I'm going to put up a little picture that kind of encapsulates all this. So I'm going to put this on top of all this, and this kind of just talks about everything that I've already just discussed. And this is in the book. But here we have activating and we have deactivating, and we have different groups. All right, I want everyone to pay special attention to halogens. They are within the deactivating class of substituents, but they are still ortho para directing. Okay, so all these groups right here are all ortho para directing groups. Okay, and then all these groups right here are meta directing, and they're deactivating. So this is deactivating, but ortho para directing. So they're not always it's not always something has to be activating and it's a particular thing. Halogens are the exception where they're deactivating but ortho para directing. Okay, just an important thing to differentiate. And so these are just different classes, different types of substituents, and where they fall in to both ortho para and activating or deactivating meta directing. And you can copy this down. It's not really needed, but if you want to see all the different types of examples of groups, it's very important to be familiar with. All right. Now what else? What else do I have to show you guys? We have all this. I think that's pretty much it, really. You just need to, I guess the one thing I could show you is kind of the order for the activating groups. There's certain activating groups that are stronger activators, and you'll have to choose which one we're going to be using as the relative one. And this all makes sense with reactions. Okay? So if we're ranking activating groups, we're going to essentially be ranking on their ability to donate, right? Their ability to donate in electron density. So that has to do with their instability as well. So this dash is going to just be the representation for the connection to the benzene ring. Okay? And then we have N, NR2. Right, we have OR, and we have things that are like this. We have N, and it's bonded to a C, right? Okay. All right. Probably should have just paused and just wrote all this out. But here's a little ordering. I'm just gonna fill in some things. So there's an O minus here. An O minus, obviously, and things that are minus. This is teach you relative to other things. Things that are minus obviously have the ability to not inductively, but to directly donate their charge for purely stability reasons, right? I have a charge, and I want to delocalize that charge, and I'm going to delocalize it by resonating with the benzene ring. So this is going to be very, very activating compared to the other things that are just simply freestanding lone pairs that don't have charges necessarily. Okay, this is just, it is not to be so fixated. NR2, can go with NH2, and it'll be much easier to differentiate between these things. OH versus OR. I would like to see why that is, but there's just little things that I memorized to help me make decisions. And I don't know how important this was when I was doing this, but you'll have like very clear differences. Like you'll have O minus versus like this group, and I have to fill in this right here. There's a carbonyl right here. This is a very, very important thing we're gonna look at later for the facts. And then we just like comparing like O minus versus an R group, or this versus an R group. It'll be very clear, what you're differentiating in between. So this is just a very brief, small order of the ranking of the activating groups. Okay, so on this side I have, most, and then least. All right, and that's essentially it for this video. Okay, next video will be reactions and just covering some of those things. All right, guys, see you in the next video.